is a major topic. As a reminder that is 25% of your exam. Out of the 100 questions, 25 of those questions will be on algorithms and computational thinking. So that is a bigger chunk than the impacts is. That's 15%, not insignificant, but not as big as algorithms. And of course, programming is the biggest chunk. So we'll spend the 2 following Saturdays, or most of them, on that as well. So what are algorithms? What is computational thinking? Can one or two of you unmute and just share that? And I know this is review if you're a computer science teacher.
Algorithm is a series of steps to solve a problem.
Excellent, thank you. That was Paula?
Yep.
How about computational thinking? Someone else?
I can take it if you'd like. Computational thinking is the difference between the way we process a problem and the way a computer does.
Sure, yeah. I mean, it's exactly what the words sound like, right? Thinking like a computer, right? And so there are some major differences, as Paula mentions, from what humans normally do, is why we need to teach it as a subject and integrate it throughout elementary and middle school as we're building more and more computer scientists, but also even just digitally literate citizens of the world, since computers are such a big part of our world, that computational thinking is important to understand to some degree for everybody. Okay. So this is sort of a summary from the Praxis, that what do you need to know about algorithms and computational thinking. I'm going to give you a quick overview of the outline for the whole unit, or the whole section, content category, and then we're just going to focus on the first 2 or 3 pieces of it today. And we'll do a lot more next week. So for algorithms and computational thinking, the Praxis does expect you to understand algorithms, develop them, maybe not so much, like be able to talk about developing or think about how it's developed. They wouldn't actually have you develop a brand new algorithm during the test. But understand them and read an algorithm and understand what's happening and analyze them is definitely a big part of it. They expect you to understand, develop, and analyze in multiple formats, including flowcharts, including pseudocode, including natural language, applying tools like abstraction, pattern recognition, problem decomposition, converting between binary, decimal, hexadecimal, and such. And they do expect you to be familiar with certain common algorithms or types of algorithms. And so it is important that you are familiar with, and we'll cover these for next week. Common searching algorithms for searching through a list of items and finding the thing you're looking for, or not finding it, as the case may be. Sorting algorithms of putting like a bunch of numbers in order, or putting a bunch of words in alphabetical order. There are some very common sorting algorithms that you are expected to understand. It's important that you understand what recursion is, as well as a couple, maybe being familiar with a few common recursive algorithms. And it's important that you have some understanding of randomization and the difference between random and pseudo-random, and how that might be used inside an algorithm. You should also be able to analyze algorithms for correctness, time complexity, how long it will take this to run in some sense, memory or storage space complexity, and understand that some algorithms are solvable and others are unsolvable. So we are going to delve into all of these terms and everything, a lot more detail between now and probably more next week. But I did want to again refer to this outline. There are 2 broad topics, part A and part B, which I sort of just summarized. So I'm not going to read those out to you again. But the outline here goes into a lot more detail. So under, that was programming. This is in that same study guide, and that's linked there. So A and B are the 2 broad topics, but then A is split into number 1, 2, 3, and 4. And B is split into 1, 2, 3, and 4. And each of those is split into these little subtopics right here, right? So understanding abstraction what do you need to know and be able to do about abstraction? Knowing how to use pattern recognition, or what do you need to know and do about that, okay? And so, for example, we're not going to get to this to next week, but in terms of analyzing sorting algorithms, it gives you a lot more detail right there. So this document should be familiar to you as a resource as you're studying. For many of you, I'm sure it already is, but just in case it's not, I wanted to point that out. Okay. We're going to look a lot more at pseudocode over the next 3 weeks because that applies to both algorithms and the programming section, that 25% and that 30% of the exam, right? So together, 55% of your exam is algorithms and programming, which not all of it, but some of it will be using the Praxis Pseudocode. So this is a little bit unfamiliar for some teachers, right? So we use pseudocode in our classes to refer to sort of something a little bit more structured than natural language, right? If you're describing how to solve a problem, pseudocode is a little bit more step-by-step if you're thinking about that Paula's definition of algorithm earlier. It's a little bit more formalized, maybe using some language like if and else and loops and some of the structures from programming and from algorithms than a normal, just natural language description of solving the problem would be. But pseudocode is not necessarily, usually when we teach it, is not very formalized. For Praxis, though, they have a formalized pseudocode that in some ways is maybe more like a pseudo language, pseudo programming language than what we would normally call pseudocode. The test programming questions are going to be language agnostic, so it should be, no matter whether you're familiar with Python or Java or C++ or Scratch or MIT App Inventor, that as long as you understand the basic things of programming and you spend a little time maybe studying that pseudocode so you're familiar with that language. And again, that's in this document after the outline. We have these boxes right here for the different symbols that will be used. Zoom in a little bit for the pseudocode, and that you should be familiar with all of these. And we're going to spend a lot of time again on these over the next 3 weeks. But it shouldn't be, you don't have to know Java to take this test. You don't have to know the specific language. All you have to do is understand general programming techniques and algorithm techniques, and maybe study a little bit of this language so it's familiar too. Again, you will also be expected to analyze and interpret algorithms that might be in diagrams or flowcharts or natural language as well. So before diving into the specific topics that we're going to start with on the algorithms, I did just want to introduce this pseudocode, make sure you all were aware of it, in case there are some of you who this is brand new to you. And I'm going to actually ask you to spend about 5 minutes for homework this week and read through that pseudocode chart or review it if you've already read through it. And I'm going to send out a survey for which of those pieces you need more time spent on over the next 3 weeks. So for example, maybe you're really good with assignment operator, that arrow, you understand what that means and don't need much time at all spent on it. But maybe you do need more talking about the array initialization and reference. Okay, so please do check your emails, look out for that survey. I might even be able to post it in the chat here when we're finished for today, but I'm sure many of you want to take a break after we're done. So again, that's mostly used in the programming, but also can be used to look at some of the algorithms, and an algorithm might be presented in that pseudocode. Any questions so far? Okay.
I have a question, Nick. and I'm currently taking a Java class. Even though this Praxis uses pseudocode, do you think that will help?
Yeah.
Okay.
I mean, from my experience taking the Praxis just last year, that I think the language that did prepare me the most was Java. That again, it's supposed to be language agnostic, but the way Java uses object-oriented language, that is one of the later pieces on it. These object-oriented keywords and classes. The way Java initializes and refers to arrays is very similar to what's here. So I definitely don't think you have to take in Java to do well on the Praxis, but I think it'll absolutely be a benefit if you're doing that. Yeah.
Okay.
And also the way Java, a couple languages do, but others like Python don't, is declaring your variables ahead of time. And so that gives you a much deeper understanding of these data types than a language like Python or drag and drop language that is sort of implicit in the how you assign that variable.
Okay.
Okay. So I wanted to take a moment and just to test our basic understanding of the pseudocode and maybe get through it, even though you might not have ever seen the pseudocode before. I wanted us to read through an example together. And this is going to be number 5 from the sample questions at this link, if you want to pull it up on your own screen, but I'll also pull it up right here. So I'm going to scroll down the same study guide document from the ETS and down to number 5. And the way they number these questions, there's only 25 right here in this free version. As Kim was pointing out, you can get 100 sample questions by paying the ETS, but they are in order by those units. So like the first 3 questions are about impacts of computing. And number 4 and 5 are some of the topics about algorithms that we're looking at right now. So you can see that they are giving an algorithm right here. So Chloe is playing a game in which she rolls a pair of dice 6 times. Her initial score is 0, and after each roll, her score is recalculated. The table shows the outcomes for each roll and Chloe's recalculated score. Consider the following pseudocode segment. Int score gets 0, or is assigned the value of 0. Int die1 gets 0, int die2 gets 0. We have a for loop, which is marked here, and then there's indentation for the body of the for loop, and then it ends with this n4 right here. We're starting with I being initialized to 0, up through I, all values up through I less than 6 are repeating this for loop. I is being incremented by 1. 1 gets the value from die1 value, is a function or procedure that returns the value of the first die. Die2 gets die2 value, again, another procedure. And then score gets, well, this new score procedure called with 3 parameters, die1, die2, score. And it's asking us which of the following answers for that new score procedure seems to match the data in the table. So let's look at each answer in turn.
So it's adding this, the score is supposed to be adding each other together and then adding it to the previous. Wait, I don't know what.
See, we're not told that. Given the data, we have to add, this is part of the algorithm section, is identifying patterns. But we don't have to just identify them directly from the data. We could just consider each answer and see which of these answers matches that data. So no, you can see clearly the first time, it looks like 3 plus 4 is 7, and 1 plus 5 is 6, and 7 plus 6 is 13. But that pattern stops, right? Because the score remains 13 even after the third roll.
Yeah.
It doesn't add anything. And then somehow on the fifth roll, it gets reset back to 0. How does the score get reset back to 0? So that, as you're saying, it eliminates A, because A is saying return the old score plus dice 1 plus dice 2. So that pattern seems to be going for the first two, but immediately stops for the third. Is everybody clear on why A is wrong? Thumbs up.
I got it.
Down. Okay. So it's hard for me to see the chat when. Okay. Yeah.
So no questions.
Okay. Looking at B. Okay. Here we have a little bit more complicated of an algorithm. And again, if you're not familiar with these symbols, we will spend more time on each of them. But the first line is the same as in part A. We first update old score to be the older old score, plus dice 1 plus dice 2. But then we have a more complicated if-else statement to change old score after that. And it says if dice 1 equals 6 and or dice 2 is equal to 6, we're gonna then subtract dice 1 and dice 2. So does that seem to match any of the data? Does that seem to match the data there, just that first if statement?
Can you scroll back up? There we go.
I had to zoom out a little bit.
Yeah.
Sorry.
I don't think so, because it would have done that on the third. It
Okay.
would have done that on the third step, right?
Well, remember this subtraction
1 of them equals 6.
is after this addition. So you first add dice 1 and add dice 2, and then you subtract dice 1 and then you subtract dice 2. So it could have done that on the third step, added 8 and then subtracted 8. So it could be. Where else could we look to see if that might be correct?
5.
Yeah, let's look at 5 where they're both 6, right?
Mhm.
So if they're 6, we should have added and then subtracted, and then we would skip the else, right? Because if you are in the if body of the conditional, that part, if that if condition is true, you do what it says here in the if body, and then you skip the else, and you would return it. So
it should stay 13. It should have stayed 13 there. It didn't. So
yeah. So B is incorrect, because if die 1 is 6 or die 2 is 6, well, they're both 6, it happens, then it would have added 12 and subtracted 12, and it should have stayed 13. So we know B is wrong, okay? Looking at C. Here, we don't do that initial adding step like we did right there. We just start immediately with an if inside this method. If dice 1 is not equal to 6 and dice 2 is not equal to 6, we will just do the addition. Else, if dice 1 is equal to 6 and dice 2 is equal to 6, we're going to return 0. No matter what the score was, we'll set it back to 0. Else, we'll just keep the old score the same, return the old score within this nested else.
Mhm.
Does that seem like it matches the data?
If
well, it works on the first and second one, but on the third one, it should have. Oh yeah, the third and fourth one, it works. On the fifth one, it works.
and on the 6th one.
Well, on the sixth one, where did it get the old score?
The old score would come from the previous score.
The 0.
The 0,
Mhm.
yeah.
On the sixth one, it should have been 0, right?
No.
So on the sixth one, it would have said, well, they're not, this one is not 6 and this one is not 6. So it'll return old score 0 plus dice 1, 2 plus dice 2, 4. Yeah.
Right,
So C is
okay.
it.
So that seems to be matching, but let's just read D to be 100% sure. That
Well,
we
the
didn't
problem
confuse.
though, the problem is when it returns 0, it doesn't actually I think it's not working because when it returns 0, it doesn't change old score to be equal to 0. It just returns 0. You see? So
Yeah.
if in that case, it's not quite correct.
So we're going to get into more how procedures work and the difference between assigning by reference and assigning by value. But actually,
Okay,
if it's
assigns it to
returning
score.
that 0 here, up here, you see where I'm highlighting?
Yeah. I see it assigns.
It'll
I
put
see where
that
it
into
assigns it.
score. So it doesn't matter about old score. Score will be set. Yeah. So that's okay. Okay. How about D? Does anyone see any problems with D if that we can conclude C is correct?
Is it the first if statement, if dice 1 equals dice 2, return 0? Because
Yeah, so that matches column 5.
But it doesn't match
But
column
here we
6.
have another dice 1 and dice 2 in column 6, and it doesn't return 0, it returns 4. So yeah, C is the correct answer. D is wrong as well. Okay. Okay, good. So that might have been overwhelming, and don't worry too much because we're going to really dive into the pseudocode. And like I said, I'm going to send out that survey to see which parts of the pseudocode you all need more time spent on.
Well, that like how to walk through it, that helped.
That was, say that again, that was a lot to walk through?
No, I said that helped. Like looking
good.
at it at first, I was kind of like, oh, I'm just going to skip this.
Yeah.
But like when you walk through it that way, that helped. Like show
Okay.
me what to look for, that helped.
So it's always good to hear that teaching is helpful. Yes. Yeah, we're definitely going to do more of that over the next 2 weeks, and we can do more in the office hours as well. And yeah, so walking through like that. And but Tanya, you're right. That it might on actually exam day, you can see, oh, I'm going to need to spend more than 2 minutes on this question. Remember, I said at the beginning that you get an average of about 2 minutes per question. But some you can answer in 1 minute or less, right? Just read the question, pick the answer. It's immediately obvious. But others like that, you're going to need 5 minutes to work on. So you could choose as a test taking strategy to mark it for, I want to come back to this later, and do the easy questions first. But yeah, so that definitely could not answer that in 2 minutes. That would be way too quick.
Hey Nick, I have a question.
Yep.
In the test itself, you said you can go back and forth, so you can kind of bookmark a question and then go back if you need it.
Yep.
Are the questions grouped together by type?
No.
Oh, so they're really.
So they are on this study guide. I was mentioning that to help you as navigate as we're studying the next 5 weeks. But no, on the actual test, they're all mixed up.
Okay.
Okay, so we're just really gonna do a tiny bit of stuff on algorithms today, since we only have this 8 minutes left. And we'll talk about the first couple topics. Picking the right, so the first subcategory under algorithms, part A, part 1, back on that outline I was mentioning, is abstraction. And again, most of you are aware of abstraction, but what that is picking some people say removing detail. I like, yes, there's some removing detail, but I like to think of it as picking the right level of detail to focus on. So that sometimes you need to dive into the very details to understand something and get it working. But other times you're happy to work up here on a higher level. And so picking that right level of detail to focus on the bigger picture for the task at hand is really what abstraction is all about and why it's useful in computer science. So on the Praxis, they very much will probably or might ask you to do something like this example here, thinking about giving you things and asking you to put them into the correct order. And again, I provided this link. You can click that later to see more info and examples. So thinking about a very basic one in computer science that is that, well, what's really happening is electrical signals are being sent through the wires or wirelessly through the Ethernet wires, right? Or if you're communicating over the internet. But we abstract that out one level up and think about that not as electrical signals, but as bits, ones and zeros. And then those bits can be combined into bytes that might be interpreted as a character or a letter. And then those letters that have been encoded from those bits are then grouped into words. And then those words are used in programming a software application. And then at the highest level, the people using that software application, not the programmers, not necessarily us, but the users interacting with it, don't have to be aware of any of those lower levels of abstraction. They can still type something in Microsoft Word without having a clue about any of the ones and zeros and the character ASCII encoding or anything that's going on underneath the scenes. Okay? So having a hierarchy of abstraction like that and possibly being able to put things like that in that order is absolutely something that might be asked. And here's another sample question from that same ETS guide that asks you to do that, but with something a little different. So I'll let you read that. Take a minute to read silently. Okay, anybody think they know the answer? So keywords up here is highest to lowest. It might be easy to reverse that and think lowest to highest. Okay. We have a vote for A. Anybody else? Agree, disagree?
I was thinking that machine language is machine specific and assembly is non-machine specific. So I was thinking B.
Okay. Anyone else? A, B?
Yeah, A.
A.
Yeah, A.
I'm gonna stick with A too.
Yeah, I think I'm gonna go with A as well. I think, sorry, I didn't catch who pointed that out, but I think you're right. So assembly language is not machine specific, or it's used by a lot of machines in common, but that means it's a higher level, right? Because each machine has its own language, that's the machine language, but to be grouping a bunch of them together, that's higher up. Remember, we're going highest to lowest. So block-based, like Scratch, down to the machine converts that into assembly language. And of course, logic gates are the lowest level presented here, because your ands and ors and nots with your electrical circuits are all printed on the circuit boards there or dynamically changed.
Thank you.
Okay, so this last slide, I wasn't really going to delve too deep into these four things, so I'll just mention them. So you should understand how to recognize patterns, including mathematical patterns, whether there's a linear pattern, a quadratic pattern in a group of numbers, other types of patterns. You should understand the basics of problem decomposition, taking a big problem and splitting it up into smaller pieces that are more easily solvable. That's going to come back when we talk about recursion next week. You should understand the basic components of algorithms, and by that, I link this here to the Khan Academy lesson on components of algorithms. And by that, we mean sort of like what is commonly found in algorithms. Iteration, right? Repeating something, looping, is found throughout hundreds, thousands of different algorithms. So that's a common building block. Conditionals, like if-else statements, are found as a common building block of algorithms. So sequencing, selection, iteration. You could also think about having a procedure or a function or a method as a common component of algorithm. And that's an example of using abstraction to abstract that out.